Thank you very much for the introduction, and thank you. I would like to thank the Eccomas community and the organizers for this opportunity to present this work about uncertainty quantification in computational mechanics. The main objectives of this work are to propose stochastic and multiscale models for hyperelastic materials. And we are especially interested in those that can exhibit large variabilities in their mechanical response, such as soft biological tissues, for instance. And as an illustration, you can see in these figures some results of tensile tests performed on samples of arterial tissues sampled from 13 different patients. And as you can see, there is quite a large variability in the stress responses. And our objective is to construct stochastic models in order to take this kind of uncertainty into account in our numerical simulations. This is the outline of my presentation in 3 sections, which are stochastic elasticity at large strains, then at small strains, and then finally a last section about surrogate models in computational homogenizations. Since we are dealing with hyperelastic materials, we can introduce a stored energy function, W, that depends on the position x and the reference configuration, and on the usual deformation gradient f. So common examples of stored energy functions are given, for instance, by the Nihilkun model that depends on the shear modulus, or by the Muner-Evelyn model that depends on 2 parameters P1 and P2. And so basically it's for this stored energy function that we would like to construct a stochastic representation. So to do so, we need a bit more information about it, and this information can be found, for instance, in existence results for the nonlinear boundary value problem. And we rely on the results proposed by John Ball in 1977, which state that if the stored energy function is polyconvex, satisfies a coercivity inequality of this form, and also a limit behavior condition of this form, then there exists at least one solution to the nonlinear boundary value problem. So, for instance, if we take this stored energy function, which depends on 3 parameters P1, P2, and P3, and also 2 exponents eta1 and eta2, then polyconvexity and coercivity require that the parameters P are all strictly positive, and that the exponents eta1 and eta2 are greater than 2 and 1.5. And we can get additional information by also linearizing the stored energy function near the reference configuration, which gives us what we call consistency relations between the parameters of the stored energy function and the elastic moduli at small strains, which are the bulk and shear moduli in this case. So basically, it's by using this information on the parameters that we would like to construct their joint probability density function. So to do so, we start by introducing a stochastic strain energy function defined on some probability space and denoted by this capital W for convenience. And this stochastic stored energy function is simply obtained by modeling its parameters and elastic moduli at small strains C by random variables, or more generally by random fields like this. And for simplicity, we assumed that the exponents involved in the stored energy function can remain deterministic, so we can just forget about them from now on. And so the strategy we adopted for constructing a stochastic stored energy function can be summarized in roughly 4 steps. The first one consists in gathering the constraints related to polyconvexity on the parameters P of the stored energy function, and also determine the consistency relations at small strains denoted by L between the parameters P and the elastic moduli C. Then the second step consists in introducing an additional random variable U and a transformation H, which just allows us to simplify the developments. And this transformation is actually it's such that the polyconvexity constraints and the consistency relations are completely equivalent to separate its sets of inequalities on this new random variable u and the elastic moduli as small strings. So this means that instead of constructing the joint probability density function of P and C, we are going to construct the one of U and C. So we achieve this by having recourse to information theory and the maximum entropy principle. So we first need to give us some kind of available information. And so we assume that the mean values of the log of all the inequalities we have on U and C are known and bounded. So this will ensure that they are all satisfied almost surely. And we also assume that the mean values of C and U are available. So this information will ensure that the stochastic store energy function is polyconvex and coercive almost surely. And so finally, we can select the probability density functions of C and U by using the maximum entropy principle, which consists in maximizing a measure of uncertainty over the sets of probability density functions that satisfy this available information. So for instance, we applied this to Ogden's class of stored energy functions for homogeneous, isotropic, and incompressible media. And in this case, we found that the random shear modulus follows a gamma distribution, and that the random variable u follows a Dirichlet distribution. And then you can retrieve the random parameters p using this transformation between the random shear modulus and the entries of the random variable u. And we applied this model to for the identification of uniaxial test on soft tissues. And in these figures, you can see the results we obtained for gray and white matter of brain tissue undergoing compression and tested at 2 different strain rates. And so we can see that the stochastic model in red lines reproduces quite well the mean values and the standard deviations of the stresses given by the experimental database in black lines. And we got similar results for other tissues like spinal cord white matter or liver tissues, for instance. The second example that I would like to present is this store energy function. The functional form is not very important, but this one is commonly used for the modeling of arterial tissues, which are depicted in this figure. And the main difference with the previous store energy function is that its parameters are modeled by random fields instead of being just random variables. And these random fields are defined as a nonlinear transformation H of Gaussian fields Xc. And in order to build this transformation, we just fix the position X and the reference configuration, and we apply the same, almost the same 4 steps as in the previous case to get the probability density functions of the parameters. So instead, I'm going to focus on the definition and the generation of this Gaussian field, because in practice, it is quite a demanding task when you have such a dense finite element mesh, because you have to be able to generate the Gaussian fields at every gauss point of the mesh. So we decided to define the Gaussian random fields as the solution of this stochastic PDE, which is driven by a spatial white noise. And in this equation, you have one parameter L that allows you to control the correlation length of the Gaussian random fields. And you also have a matrix H that will allow you to control the anisotropy of the covariance function. And what's interesting about this equation is that it can be solved by the finite element method using the same mesh as the one you're using for the mechanical problem. And by computing the classical Galerkin approximation, it can be shown that the nodal values of the Gaussian field follow Gaussian distribution, and the inverse of its covariance matrix, sometimes called the precision matrix, can be written in terms of the stiffness and the mass matrices obtained by assembling the Galerkin approximation. So in practice, we just have to assemble these matrices, which are sparse, so it's quite fast, and then generate the Gaussian field at the nodes of the finite element mesh, and then we can obtain its values at any Gauss point using the usual shape functions. So for instance, in these figures, you can see some examples of generation of one Gaussian field in the arterial wall I presented earlier. So in the left column, we chose H such that the Gaussian field is highly correlated along the longitudinal longitudinal direction of the artery. So you can see that here you can see one realization of the Gaussian field, which is highly correlated in that direction. In the middle column, you can see a Gaussian field which is highly correlated in the circumferential direction. And in the last column, we imposed a locally isotropic correlation function. So these figures are meant to illustrate that with this approach, you can have a very flexible covariance function in practice. So as an illustration, we considered a boundary value problem in which we applied a pressure on the inner surface of the arterial wall in order to model the blood pressure. The inlet of the wall is totally clamped, and the outlet is able to slide in its own plane. We used a three-field formulation in order to avoid locking phenomena together with a static condensation, and we implemented all this in Sandhya's tree-nodes package in order to accelerate operations. And for instance, here you can see 4 samples of the von Mises stress field inside the artery, and below you can see the probability density function of the maximum value of the von Mises across the artery. So all the realization exhibit the same kind of localization pattern, but this is because we didn't put any uncertainty on the fibrous direction that are in the arterial wall. So I can discuss about it afterwards if I have time, if you want. Okay, so that was it for stochastic elasticity at large strains. So in this second section, we're going to place ourselves under the assumption of small strains. And in this case, constructing a stochastic storage function is completely equivalent to constructing a probabilistic model for the usual first order elasticity tensor, A. And in practice, it's even more convenient to work with a matrix representation of this tensor by using Voigt's notation, for instance. So it gives us a 6x6 random matrix, which, due to the symmetry properties of the material under consideration, satisfies some invariance conditions like this. And so it has been shown that in order to have a well-posed stochastic boundary value problem at small strains, we need to have a uniformly continuous and coercive bilinear form in the weak formulation, and we also need to have a random elasticity tensor with bounded second-order moments. So in order to achieve this, we proceed in a few steps, just like for the stochastic storage function. And the first step consists in introducing this algebraic decomposition for the random elasticity matrix, where epsilon is a small parameter, and the lowercase a matrix is the mean value of the random elasticity tensor, and M is an additional random matrix which has a mean value equal to the identity matrix and which is positive definite almost surely. So with this decomposition and these properties, we will ensure that the bilinear form is uniformly continuous and coercive, so that the stochastic boundary value problem is well posed. So at this stage, we can state that the available information we have regarding M is given by its mean value equal to the identity and by its positive definiteness, which we take into account by assuming that the mean of the log of the depth of M is known and bounded. So this will ensure that M is positive definite almost surely. But we actually have more information about M because we know that it has the same symmetry properties as A. So for instance, if A is an isotropic elasticity tensor, then M is isotropic too. So for instance, if we consider a transverse isotropic material, then M can be decomposed onto the so-called Walpole basis. So for transverse isotropic symmetry, this basis has 5 elements, E1, 2, 3, 4, 5, which can be found in the literature. And so instead of constructing the probability density function of M, we are going to construct the probability density function of these coefficients on the basis. And what's interesting about this decomposition is that if you introduce this small 2x2 matrix, which gathers the 3 first coefficients in a symmetric fashion like this, then it can be shown that M is positive definite if and only if N is positive definite and the 2 remaining coefficients not included in this are strictly positive. So using this property, we can it can be shown that the available information we had on M can directly be reported on N and the scalar coefficients M4 and M5. And so without going through all the details, by applying the maximum entropy principle again, it can be shown that N follows a SD0 plus distribution, and the remaining scalar coefficients follow gamma distributions. And what's interesting about this result is that these are well-known distribution, well studied in the literature, so there exist simple and efficient random generators for such random fields. And it should be also noted that this trick can be generalized to all symmetry classes ranging from isotropic symmetry to triclinic symmetry. So as a very small numerical illustration, we use this random field model for a composite plate made of 32 plies. And here you can see 2 samples of the von Mises field and 2 samples of the 2-2 component of the deformation tensor in the composite plate. Okay, so what time is it? I have one last section which is a bit different because it deals with the surrogate models for effective store energy functions in computational homogenization. So more precisely, we consider this kind of structure, which is made of heterogeneous hyperelastic material, and we use the Fe square method in order to solve this 2-scale boundary value problem. Which consists in assuming that at every gauge point of the structure there exists a representative volume element which can be used to solve a microscopic boundary value problem to get the effective store energy function that is used to solve the macroscopic problem. And in practice, such approaches like Fe square, MSFM, or FEHMM are quite expensive, even for 2-dimensional problems. So we wanted to investigate approximations for this effective store energy function by using polynomial approximations and projection onto specific families of store energy functions. First we use the Hill's definition of the effective store energy function, which is obtained by solving the microscopic boundary value problem on the representative volume elements using this kind of linear boundary conditions where F bar is the macroscopic deformation gradient. And in practice, it's more convenient to express this effective store energy function in terms of the entries of the white Cauchy-Green tensor, because it reduces the dimension of the space we want to interpolate. And so it's for this function that we are seeking approximations or surrogate models. And the first one we investigated is a polynomial approximation. So we are looking for an approximation of the effective store energy function which is uniformly accurate over a set of macroscopic loadings gamma, which is included in the set of positive definite right Cauchy-Green tensors. So to do so, we define the uniform measure over gamma, and we introduce the space P lambda P, which is spanned by the polynomials which are orthonormal with respect to this measure. And in this definition, lambda P is the set of multi-indices with a norm less or equal than P. So here P is basically the maximum order of the polynomial interpolation. So we can define the polynomial projection of the effective Story function on this polynomial space, and we get this kind of polynomial expansion where the coefficient z alpha can be computed by taking the inner product against the polynomials. And for instance, in the two-dimensional case, we only have 3 microscopic loadings, and we can use a Gauss-Legendre quadrature rule in order to compute these coefficients with NQ integration points in each direction. So we applied this to this two-dimensional RVE using Nehookian models for the matrix and for the inclusions. And here you can see the results of a convergence analysis with respect to the order P of the approximation and the number of quadrature points for the quadrature rule. So for instance, if you want a L2 error below 10 minus 10, you need an order P equal to 15, and you need at least 14 integration points in each direction. So for instance, in these figures, you can see absolute errors between this between the true effective Story function and its polynomial approximation for a simple tensile test in the left panel and for a biaxial tensile test in the right one. And we also compared our approximation to another one available in the literature, which relies on cubic spline interpolation. And we observed that even for only 13 points in each, 13 integration points in each direction, we are able to obtain a quite accurate approximation with this polynomial expansion. But the main issue about this approximation is that it cannot easily be extrapolated because it overfits the set of macroscopic loadings that we gave ourselves. So we wanted to test another projection of the Story function by defining a set C, for instance, of Story function that can be written as a linear combination of function V, which represents some specific classes of Story functions. So for a Nehookian model, for instance, you will have 2 functions, V1 and V2. And the objective is then to determine the coefficient by j here by minimizing the L2 error between the effective Story function and functions belonging to this space. And so for instance, for this RVE again, we tried to compute the closest Nehookian model to the true effective Story function. And we gave ourselves 10 sets of macroscopic loadings gamma with increasing sizes in order to investigate its influence on the projection. And we found that the L2 error and the parameter solution to the projection converge very quickly with respect to the size of the set gamma. So in practice, it means that we can use a very small set of macroscopic loadings in order to compute this projection, and so it reduces the computational cost compared to the polynomial approximation. So if we go back to our full structural problem, in the left you can see the von Mises stress field obtained by the Fe square method, which we take as our reference solution. In the middle figure you can see the stress field obtained with the polynomial approximation, which is quite accurate but quite expensive too. And on the left you can see the solution obtained by using the closest Nehookian model to the effective Story function. And so essentially it underestimates the stress field, but this one has been much cheaper, only a few minutes to compute actually. It can easily be extrapolated for other macroscopic loadings, and it can be used in any finite element software. And we also think that it could probably be improved by considering more sophisticated sets of Story functions to build this approximation. Okay, so in summary, we propose stochastic models for hyperelastic materials by relying on information theory and the maximum entropy principle in order to take into account constraints related to existence theorems in nonlinear elasticity. We also proposed a unified class of Wendell field models for elasticity tensors. We worked on inverse identification procedures for soft biological tissues submitted to uniaxial tests, and also for carbon reinforced composites when the experimental data is given by partial field measurement, but unfortunately I didn't take the time to speak about this. And finally, we also investigated functional approximations of effective store energy function in view of propagating the uncertainties across cases. So thank you very much for your attention, and thank you again to Eccomas and the organizers for this great opportunity. Thank you.